The cosmos is filled with mystery. Mysterious objects, mysterious physics, mysterious stretches of outer space filled with chaos and cataclysmic events. In fact, the only thing more infinite than the universe is the number of mysteries and enigmas contained within both the observable and the unobservable. Two of these lingering mysteries are actually two of the most popular aforementioned entities, the two things that might demand more questions than answers, and have more interest from you or I than actual knowledge by astronomers. These two mysteries are dark energy and black holes, topics you've probably heard about but still don't quite understand. If you don't, you're not alone. As mentioned, some of the brightest minds in the world and the most passionate researchers on the planet can't explain black holes and dark energy that may or may not even exist. But what if we were to tell you the keys to each entity might be hiding within the other? That dark energy and black holes might be gargantuan unknowns of the universe, but also might be related so closely one cannot exist without the other. It might sound as crazy as the cosmos can be, but theories are surfacing that demand we take a deeper dive in the question that's making the rounds. What is the relationship between black holes and the property we refer to as dark energy? Before we dive into the black hole-dark energy connection, we should take a singular look at each of them. The first thing to know about dark energy is that it's a hypothetical form of energy, and is not a proven, observable property of the universe. Rather, it's the name used for an unknown energy that constitutes an estimated 68% of the total energy in our observable universe as of 2022. This unknown energy is also the leading force and the explanation for the rapid expansion of the cosmos. In other words, something relevant out in the cosmos, something that makes up more than half of everything out there, is causing the universe to grow larger and faster. Dark energy is simply the signifier. The hypothesis of dark energy was born under Einstein's teachings of a cosmological constant. This cosmological constant was theorized as a way to create a solution for the gravitational field equation suggesting we live within a static universe. In this scenario, gravity would require an opposing energy to fulfill negative masses that Einstein proposed filled the totality of interstellar space. Of course, it was later understood that the universe is in fact not a static entity, but rather either a contracting or expanding entity. Every time the universe expands, it releases vacuum energy, another name for a cosmological constant or dark energy. This type of energy remains whole as the universe continues to expand, causing the expansion to continue at an accelerating rate. Dark energy comes with a very speculative and mystifying nature. The density of dark energy remains very low, along with an incredibly low reading of mass, equating to something like 10 to the negative 27th power of kilograms per meters cubed. Anything of this size, but especially an unmassive energy, would be indetectable to researchers in a laboratory setting, even with all of the modern-day technology at their disposal. Another quirk making dark energy's nature unrefined is its overall lack of interaction with other fundamental forces seen throughout the universe. The only force it seems to counteract with is gravity. You might be wondering how something lacking so much density and mass can make up 68% of the universe, but therein lies the evidence of its own existence. The fact that 68% of the universe is considered empty space would be illogical when considering the measured geometry of space we've calculated. In other words, the mass and density of dark energy is needed to reconcile these vacuumed spaces, regardless of how light or small it might be. Supernova are also considered to be breeding grounds for evidence towards the existence of dark energy. They are used as standard candles, so to speak, measuring the age of the universe based on supernova's objective distances and redshifts. Using supernova and their luminosity readings as a way to measure the expansion of the universe, these calculations end up with a universe 71.3% made up of dark energy. This is just a 3% increase from our current estimate based on various other data points. Dating back to the late 1950s, it is widely believed black holes are massive stars that collapsed in on themselves. These processes would then deform spacetime and create an event horizon, or in other words, a boundary of no escape. This means that objects can go only in one direction in and around black holes, and with their incomprehensibly low temperature, they are directly unobservable. The makeup of black holes to this day is an unsolved equation, but most experts agree they contain only three independent physical properties: mass, electric charge, and angular momentum. If an object enters the black hole, it ceases to exist, at least from an observational perspective. And because the parameters that make up a black hole do not change, it is impossible to discern what exactly enters or has entered a black hole. There are also black holes out in the cosmos that only contain mass, rather than three separate conditions. These are known as simplistic black holes, and have the same gravitational field as other spherical objects of the same mass. If an object is far away enough from the black hole, it will not be agitated by its gravitational pull. Depending on the black hole, these cosmic destroyers also contain what are called gravitational singularities at their center. Singularities are the specific point wherein the intensity of gravity is so high it causes spacetime to break down beyond identification. In a non-rotating or non-charged black hole, all that passes through the event horizon or outer layer cannot avoid being sucked into the singularity. Those objects may attempt to retreat, but can only do so for so long before ceasing to exist as they are crushed into the previously mentioned infinite density, and their mass is added to the totality of the black hole. In a rotating or charged black hole, being pulled into the center is not inevitable. If an object were to theoretically avoid the singularity and exit the black hole, the potential to enter a completely different spacetime exists, making the black hole a wormhole. However, the existing object would most likely not arrive at the other side of the wormhole in the same form or image that it was in when it first entered the wormhole. This is the same reason why, despite the mathematical possibility of returning to one's own past using closed, time-like curves in a rotating black hole, the rules of quantum physics combined with the other theoretical paradoxes, such as causality and the grandfather paradox, make time travel also as unlikely as finding new universes. Do you immediately see any sort of connection the two might have with one another? They are both unobservable to the naked eye, were born from theoretical astronomy rather than a happenstance discovery, and are located hundreds upon hundreds of light years away from Earth. They also both carry direct relationships with gravity, as they constitute the two most drastic forms of the equation. Black holes have nearly infinite gravity, while dark energy is the vacuum form of gravity. It's why scientists are growing more and more curious about the idea that black holes are the source of dark energy themselves, which would make black holes the main perpetrator in the vast expansion of the universe. Essentially, this theory claims that during the process of large stars collapsing and then dying, the normal matter of the star is compressed into a near infinite small size and near infinite density, before releasing back into the cosmos as dark energy. It was first proposed by a team of international astronomers in a publication called the Astrophysical Journal Letters. Within the letters was a study focusing on comparison between dormant galaxies and young galaxies. The team noticed that both young and dormant galaxies, galaxies in which stars still develop versus stars that are no longer being born, respectively, featured black holes with consistent growth. In a young galaxy, this growth would make sense. With new stars still being born, the explosion of matter would feed into an already existing black hole, causing them to expand. In dormant galaxies, however, the dominating thought was that these black holes would also become dormant. Instead, they are still growing, and up to 20 times their expected size at that. To make sense of it, astronomers are now pondering the question: do black holes grow as the universe grows along with it? If this were to be the case, dark energy existing at the center of black holes would make for the perfect explanation as to why. That is, a perfect expansion for some. Not all in the community are as certain a relationship between black holes and dark energy exists at all. The biggest question some researchers have for the team behind the Astrophysical Journal study is how black holes can expand the entire universe as they attract everything and anything around them inside their center. Other professionals don't necessarily refute the theory, but are skeptical that a more mundane reason isn't the cause of such a celestial anomaly. They believe that the principles of fundamental physics do not support the presence of dark energy at the core of black holes. Of course, the opposing theory is just as worthy of scrutiny, with the alternative suggesting black holes don't evolve the same way now that they did billions of years ago. Either way, neither theory can be proven or refuted. Rather, astronomers will need to go back to the drawing board and learn more about both mysterious entities if they can. And one day, hopefully, we'll be able to make more sense of the two most enigmatic things in our universe, and if they've truly been working side by side the entire time.